It's 3:31. We're a bit late, but it's better to wait for everybody to show up. Some commentary about the homework. I was told that the Friday's recitation is not very productive because even a few days before the due date, doesn't seem anybody actually has bothered to look in the homework. As a result, there are no questions, no discussion, nothing. And I realized that TA just comes and 10 minutes later he's back to his office, disappointed that he hasn't done much to help you. Okay? So that to me implies that you need more homework with shorter deadlines. Right? I mean, how else can I interpret it? Because, I mean, I know how these things work. If we give you anything and it says due in 3 weeks, you're not going to do anything until week 3. I mean, that's a fact of life, right? So, so the homework is going to be coming, and it's going to be more interesting. Okay? I don't think up to now the homework is difficult because most of the things we're asking you, you can find them here and there, literally. Okay? So we effectively want you to spend some time thinking about these things and make them to work, but they're really, it's a material that's already out there. Okay, so we have to spend maybe a lecture or two on regression problems because sort of is one of the most fundamental problems in computational statistics, and we can make useful practice of some of the Bayesian inference tools we have learned up to now. So, obviously, my job is not to make you bored, especially those who think they know everything about regression. So I always have to throw some things that they are new even to somebody who maybe took 1 or 2 or 3 classes in regression. Because always there is something new to learn, okay? Certainly there will be something new to learn in homework 3, because in homework 3 I'm going to ask you to do Bayesian regression and selection automatically of basis functions using sampling methods. So, and the problem will be high dimensional as well. Okay, not in 2 dimensions, I think it's like in 10 dimensions or 12, maybe even a little bit more, okay? So we need to discuss about those ideas. All right. So a lot of the topics to start today, there's absolutely nothing new. So we discussed about polynomial regression. And what I wanted to tell you today, maybe we hinted this in the previous lecture, that when you write your regression function, instead of using x squared, x cubed, right? X here is a high dimensional input space. You can use basis functions, phi1, phi2, phi m minus 1. So these are basis functions of the input. This model is still called a linear regression model because the linearity refers not to these functions, which can be, and they are nonlinear functions, but to the linearity refers to the coefficients W0, W1, etc. That's where the word linear regression comes from. Okay, so this is the notation basically that you will see in the notes in the next 2 lectures or so. W transpose phi of x. And so phi of x is the vector of all the basis functions. And you may notice here, because I have this biased constant term W0, I put a dummy basis function equal to 1 to make it to look in a nice form, you know, amenable to calculations. But in reality, even though this looks nice to denote the regression problem, we really have to do something special about this coefficient W0. Okay, so hopefully I will tell you about this. Okay, so now what basis functions you can use and what basis functions people use. We discussed polynomials. Very common is to use Gaussians, basically. So these are radial basis functions, these Bell functions centered around different points with some spread that is defined by S. Now, you can pre-assume what this mu and S is, but in reality, you should try actually to make everything in your problem, including the parameters in your basis functions, parameters to be calibrated. And how do you calibrate them? By the evidence in your data. So, you may have a very large-scale optimization problem, so you don't really need to assume this to be constant. As a matter of fact, in some of these codes, if you play with these coefficients, you will see that you can get really miserable results depending what choices you make. So you don't really want to be the one having to choose these things, okay? You can use sigmoids, all right? Sigmoids look like that, and we will see a lot about sigmoid functions. This is sort of equivalent because of the dependence here, using tan hyperbolic basically instead of sigmoids, but sort of the same functions. Okay. So let me, there is nothing new up to now. This is just basis functions. So we discuss about Gaussian noise in our likelihood, all right? So this is our regression function, okay? And we analyze this using a Gaussian noise. And we didn't really prove it, right? But this sort of model where this function becomes the mean basically of our response at every x corresponds to minimizing the square loss between this model and the data that we have. If I have time, I'm going to come back to explain this. They're a little bit non-Bayesian terminology, but you can appreciate from the least squares problem that effectively this is how we get W by minimizing a square loss function. So I give you here a typical regression problem where the basis functions, the regression function in 2 dimensions looks like this. So monomials in X, but here you can see I have quadratic terms, x1 square, x2 square. So the response obviously looks very different. The data sets are exactly the same. So actually, if you are going to write a little code, you can have the function specified by the user, and with the same code, you can solve this problem, or you can use sigmoids or whatever else of interest. Okay, I'm going to go rapidly through the next few slides because we already have seen them, but I want to modify things a little bit. So we talked about, this is our likelihood. We collect n data points, x1 to xn, with response t1 to tn, so the likelihood looks like that. W is unknown, beta is unknown. So if you take the log likelihood with these parameters theta, w, and beta, you can maximize the negative log likelihood, all right? So if you write this explicitly, then you get sort of minimizing this error function that measures the distance of your regression function from the values tn at each of the input points, okay? So this led to the least squares problem, okay? And so I'm going to tell you, just from an MLE perspective, maybe some models that you can do a little bit better than this square loss function. Okay, so before doing that, the general regression least squares problem is basically solving the system of equations you see on the top, where this matrix phi, the design matrix, is basically computed by evaluating the basis functions at each of the input points. This is input x1, so each row is one input point, x1, x2, to xn. Take a good look at this matrix because I'm going to use it as we go along, all right? This is not just for regression problems. This matrix appears everywhere in our computational statistics course. So this is, each column corresponds to a basis function, phi 0 to phi m minus 1, and each row corresponds to evaluating these basis functions at a given data point. So when you do the MLE, effectively you have to solve a least squares problem. And the matrix problem looks like phi transpose phi w equal phi transpose t. T is the vector of the given y values at the given x points. And phi transpose phi inverse phi transpose is what we call this Moore-Penrose pseudo-inverse matrix that you may have seen in this squares type of problems. Okay, so I'm going to, when I do my algebra with this matrix phi, sometimes I will be operating on each data point, so you have to think of rows. Sometimes I will be operating on the n-dimensional vectors defined by each basis function evaluated at the endpoints. So if you see something that's n-dimensional, you always think columns. If something that is m-dimensional, you think rows. All right, I think we already mentioned that the noise also can be calculated with MLE, and so the precision, beta is the precision, so 1 over the precision is given by a sample variance, right, between your data and your regression function. And that W there, to put it explicitly, that W is your MLE estimate. All right, that's why this calculation is not very good. All right, so before I tell you some, so these models that we have done up to now with least squares, they have a problem, and let me just go back to this. The problem is, if I can go back here, the problem is that we assume a Gaussian noise, and assuming Gaussian noise led to a likelihood and to a loss function that is quadratic to the error. So if you have, let's say, some point x and the corresponding t, that they are outliers, this function will penalize you significantly and will switch the regression line away from where it's supposed to be, where the bulk of the data points are. So I'm going to come back to this and show you how you can actually modify this by using some different sort of error functions by effectively playing with the noise beta. Maybe we should not use Gaussian. So before doing that, let me come back to this basis function phi 0 that we set equal to 1, or this bias term. So especially when we do regularize the squares, which is going to come shortly, right? You don't want to regularize this term here because this term is happy, can be computed very stably from the data without regularization. So what you need to do is you need somehow to get rid of the bias term before you do any least squares or any Bayesian inference. So you don't usually see this explicitly in textbooks because everybody sort of centralizes the data the way you did in homework 1, so somehow this term never really appears there. But let's see how we can explicitly calculate the bias term before we do the regression problem. So what I have done here is I wrote my regression function as a summation from 1 to m minus 1, and I put explicitly the bias term W0 there. Okay? I put it explicitly because what I can do is I can minimize this with respect to W0, and if you take the derivatives and you set them equal to 0, you get a nice formula that tells you what W0 is. And the nice formula tells you that the bias term is the average of your responses at all data points minus the weighted response of your regression problem calculated at the average basis function values. You see that? It's interesting. So again, T bar is the average of all your responses at all data points, and this is what the regression function will give you but your basis functions are computed not at 1 point or 2, but as the average at all points except. This, there is no magic in the calculation. If you take the derivatives equal to 0, this is what you get, okay? So effectively, you can evaluate W0, all right? You can evaluate W0 from this formula, and it does not have to be part of your least squares or Bayesian inference problem in general, but obviously to use this formula, you need to know W, and this W will have to be calculated by other means such as least squares, regularized squares, Bayesian inference, etc. So we will close this circle later on, but obviously now we realize W0 can be moved out of whatever algorithm we decide to use. Okay. So let me I see one of my slides that I want to discuss. It is a little bit out of order, but let me jump on this. So when we discuss about the least squares problem, right? We evaluate all these W's, all right? We set the gradient equal to 0, and we get a linear system of equations to compute for W, but also we can use stochastic optimization, and we can use stochastic optimization one data point at a time as it comes. So this is basically effectively Robbins-Monroe again. You remember I told you it's the most famous algorithm in machine learning, okay? It says you can update, as you get data points coming one at a time, you can update W by using the gradient computed at each data point coming in. And, well, it was in the previous slides, the overall gradient with respect to W is summation of this term that you see here, overall data points N. So the gradient of E with the minus sign here is basically evaluated at 1 point N is this expression. It's how much error do you do in predicting Tn with your regression model where W is evaluated at the previous time step times the basis function at point xn. This is universal sort of this type of form, right? Some error where you evaluate your model at the new data point using the model parameters from the step before times a basis function evaluated at the new point xn. So you can, rather than doing least squares and solving the least squares problem, what actually you can do, you can update W iteratively, one data point at a time, and you will see that this algorithm really works. And this coefficient eta is a learning parameter, and you will need to adjust depending on how much noise you have in your data. But the nice thing is, these algorithms work ideally when the data are noisy. All right, so if you have noise in your data, that's what you're being advised to use, okay? And so I call this Robbins-Monroe, but other names, it's least mean squares algorithm or LMS algorithm. So if you search on Google, you will find a few thousands of citations on different versions of the LMS algorithm. Okay, so let me go back to the problem where we don't use Gaussian noise and we don't use a loss function that looks this quadratic because it's not good for you sometimes. So here, I don't want to elaborate on everything, so this is what we have done up to now. So we want to use, so we had quadratic error function, loss function. How about if it is an absolute value? So the norm basically that we use is not L2, but is L1. How can we use an L1 norm? Well, if you use a likelihood model that is a Laplace distribution, and I indicate here what the Laplace approximation, the Laplace distribution looks like, there's an absolute value of t minus y minus our regression function. So effectively, our loss function would be summation of this absolute error that you do at each data point. Okay? So Yes, I mean, this function still penalizes you if you have outliers away from this line, but somehow it doesn't move this line to adjust to these outliers, all right, that you see far away. So these are your regular points, and somehow you have these weird points far away, but you notice using this Laplace likelihood error model, the regression functions don't change very much. You see, this is least squares basically is pushed away towards the outliers, but the Laplace likelihood doesn't switch very much, and this is student t, the red line. We actually, the robustness of student t has come up in some earlier lecture as well. There is some other approximations that you can use, you know, away from this Gaussian noise, so you can read more of those in the notes. Okay, so let's discuss about a little bit about regularization. All right, so we mentioned that effectively when you use regularized least squares, that phi transpose phi matrix becomes basically lambda times a diagonal matrix identity. So effectively, you know, the ill-posedness that you may have on inverting phi transpose phi, you know, this is supposed to be well posed, right? But it's not very stable to noisy data. So regularization lambda edit in the diagonal basically makes this a stable process, okay? So when you do this, the model complexity, even though it is still controlled by the basis functions phi that you have inside that matrix, it is mainly controlled by the regularization parameter. So we need to discuss it a little bit more so I can give you a sense of what you may read and see more in forthcoming lectures. So this is a general regularization term, more in the context of machine learning, not what you will see in mathematics. And it involves, so we have these W's, so we want to force them not to take very high values, because you remember when this becomes unstable, W goes very high number, plus, minus, plus, minus. So we want to penalize very large W's, and the way to do this is by augmenting a loss function with this regularizing term. Okay, so lambda is the regularization parameter, and this norm here involves the absolute values of this, each of the coefficients W's to some power Q, and I give you some regularization, so some contours basically of the regularizer for Q equal 0.5, this is for Q equal 1, for Q equals 2 is basically our Gaussian model, Q equal to 4 looks like that, and I want to concentrate a little bit on Q equal to 1, because Q equal to 1 leads to you know, to the Lasso algorithm, basically, which is sort of one of the most historical important algorithms in machine learning. So let me tell you what happens when Q equal to 1. So if you think our Gaussian noise model or our likelihood model gives you basically circles as contours, because we take that the noise beta is the same in every direction. So this is our unregularized error function, okay? So if you go and you impose the constraint that, you know, you have to satisfy, so you add in your loss function, in addition to the error that you had here, you also add a constraint, and here I'm using the Lasso constraint effectively. You notice immediately that some of the W's are forced to go to 0, okay? So this algorithm not only simply it regularizes the problem, it actually enforces sparsity. So if you have a lot of W's, some of the W's actually will come to be not very important in the overall analysis, and so Lasso algorithm explores sparsity. Now, if we have time, maybe actually on Wednesday, I'm going to show you this in the context of the Bayesian analysis, to show you how from the likelihood model you can get the posterior well-behaved by using this analog of this Lasso regularization. So keep that in mind. There is a proof actually in the notes that if you penalize, you know, if you use a regularizer of this form, that actually indeed some of the w's will go to 0, but more or less what you see on the graph is what you need to know. Okay. So let me, I'm only going to mention this, okay? We don't have to discuss all the details, but someone may say, how can I use this MLE estimates, all right? And of course, we will go back to Bayesian regression shortly. How do we use this when my output is multi-output? So, so T is not scalar. How about if T is a vector? So for every high dimensional X, right, my input can be in 10 dimensions, I get a T that is maybe in 3, 5 dimensions. How do I do this? So the obvious way will be to use exactly the same likelihood model, but instead of W being, before we had W transpose W being a vector of weights, now you are going to have a matrix of weights, right? Makes, sense. And so you are going to have a multi-output regression model, but here to make life easy, I am using the noise parameter to be shared basically by all the outputs. Actually, you don't have to do this, and maybe what I can do is, since I'm not going to give you any proof, we can go directly to a case where you can actually complicate a noise model. So you can put a full covariance matrix sigma there, all right? So really the outputs here are all coupled, okay? And so this is your general multi-output problem, and it will be of interesting to show you how do you do maximum likelihood, what comes out when you do MLE. So if you follow the standard procedure and you take the likelihood, take the derivatives with respect to this matrix W equal to 0, and of course the same thing with respect to sigma equal to 0, you get the following interesting thing, that the sigma comes to be effectively the empirical covariance, all right? This is similar to what we had for scalar output, but it comes out that every column of W that corresponds to each of the outputs seems to be basically independent of sigma, okay? So in principle, for this formulation, is like having, let's say we have a k-dimensional output, k-dimensional independent regression models, okay? So the MLE estimate for this problem is not very good because it doesn't really couple the regression problems, and this is sort of, you can see, this sigma, even though you have the impression it may couple all the W's, well, unfortunately, when you compute the W's, there's no dependence on sigma, okay? So, but still, if you want a lousy way to do multi-outputs, this is a simple way, and you can do maximum likelihood based on that. All right, so we are done with the least squares, and let's go back to our Bayesian problem. So this is the likelihood model, exactly as before. We take the noise to be scalar, so the precision beta is a known. But now for W, I'm going to make it interesting, and I'm going to take a very general Gaussian with some mean M0 and some covariance S0, okay? If you multiply the likelihood, you multiply the prior, you close the square on W, then you get a posterior that looks exactly in the form that you see down there. Again, if you don't do this calculation a few times by hand, you're not going to learn very much from this process. Okay? And I'm going to force you on homework 3 to do this type of calculation on some problems that the formulas look very complicated. Okay? But in principle, they don't involve anything beyond on closing the square that you see here. I mean, can you imagine if you multiply this and you say, I'm going to numerically sample from the posterior without actually realizing that the posterior is a Gaussian? That will not look very good. All right? And why it will not look Gaussian? Because you were too tired to close the square. That's a nice expression, right? Tired to close the square. All right. So you can see here that the variance basically in your posterior is the one from the prior plus the one that comes basically from the noise in your data. Okay? And in some statistics books, actually, they derive this directly because the two things are coupled linearly together, so you can see that, I'm not going to go through this, but basically, this is a linear model, so you can extrapolate this expression right away, but it's better to derive it. All right. So the proof is of what was in the previous slide is given here. I took the time to close the square. And the way to do this is to type it, because if you type it and you do a mistake, it will come and say, sorry, this calculation doesn't look very good. Now, some of you, I noticed, don't have computers, so don't like typing, right? And most probably, if you don't like typing, the number of mistakes in your homework will be about 10 times higher than if you type these calculations. As I say, it builds character when you type these things, all right? It builds character. There is a philosophical expression there, but, there is something to learn. If you take the time, if you take 10 minutes to do this, right, you'll be looking at this equation for 10 minutes. Something will come out from it, okay? I know you don't believe me, but something is going to come out from it. So, this is the posterior. Obviously, the map estimate is MN. Okay. Interestingly enough, for those who like online formulas, like many things in machine learning, you can actually update the mean and the covariance sequentially. So if you know estimates of M at time Tn, when you have collected n data point, up to n data points, and you know the variance, you can actually update things, going from n to n plus 1 using these very nice formulas. So you don't really need to compute all of this thing for all data points and then invert it and all of these things. No, you can just do this one data point at a time. If your data points are high dimensional, this is an extremely efficient sort of calculation. I wish you can do this in all the problems, right? But certainly I suggest that you look in your problem. If you can do this sequentially, this is the right way of doing it. Okay. So this is what we used in the lecture last Wednesday. So if your prior is a spherical Gaussian with the same alpha basically used for all the W's, then this general model, if you plug in things, it gives you your regularized least squares. But obviously our model is much more general, right? You can see this is a much more powerful model. But obviously the question will be, what do you use as a mean for your prior and what you use for S0? All right, so let me go back to the data centering so I can finish this discussion on what we need to do with the bias term. And I'm going to give you sort of two different type of approaches, very different, and they achieve sort of the same task on their own merit. So as a first approximation, let me do the following. You may not like this approximation, but it looks complicated, but it's actually not. So let's say that I split the bias term, all right? I just put mu here to indicate the bias term is really the mean of my responses, so it's a mean vector. And this phi W, this W is only, it doesn't, so it has my real basis functions, not the basis function phi 0 that's equal to 1. all right? So I'm writing my likelihood model in this expression where I remove the bias term outside. So we're going to center the data, exactly as we discussed before, and the way we're going to center the data is you're going to look in each column, and you're going to remove basically the average, all right, computed over, for each basis functions, compute over the data set points, okay? And so this is the constraint that you want to impose as pre-processing. So before we do anything, we're going to impose this constraint on this matrix phi, okay? We don't really lose anything, so we're going to impose this constraint. Then what do we do with mu? All right, how do we calculate the bias term? So I'm going to give you, I already gave you actually one sort of approximation where you compute the MLE estimate of mu, but let me do something different here. How about if I consider mu as an unknown random variable or random vector, and I do my predictions for W by integrating mu out. So in other words, how about if I take mu to be coming with some uniform prior, and then before I do the predictions for W, I integrate mu out. In other words, mu is unknown, so rather than solving for mu to start with, right, how about if I integrate mu out? Is that okay? Can I do this actually? Well, I'm not going to go through the algebra because really there is, and again, you may be looking and say, wow, too complicated. There is really nothing, okay? So, I subtracted this term. This is the average of the responses, and I add it, and then some modifications. And then it comes out, all right, with data that they're centralized, as I indicated in the previous slide, that if you put a prior on mu that is uniform, and you integrate mu out, so you notice here in my likelihood model, there is no mu anymore. Why? Because I'm going to average over all possible values of mu. And how do you compute an integral where you have to integrate on mu? What's the buzzword again? What is an easy way to integrate on mu, especially now since we play with Gaussians? Complete the square on mu and get the normalization of a Gaussian. And then when you do that, by a miracle, it comes out that the likelihood model looks exactly like our Gaussian likelihood model, where instead of t, we use the centralized t. So the model actually, you know what, if you centralize the responses, not just the basis functions, the likelihood model looks identical to what we had before, but this W does not involve the bias term. I don't know if this approach makes any sense, right? So basically, in our regression model, we had W0 plus the first basis function times W1 and the second times W2. We got rid of W0 completely by centralizing the responses T and the basis functions, this design matrix phi, and in addition, by averaging over all possible values of mu using a uniform prior on mu. So really, we don't have to do an MLE or anything like that, all right? This procedure gives you exactly your regular least squares problem, or whatever regularized least squares, or Bayesian inference, whatever you're going to do, all right? And somebody may ask you, well, but I want to know what the mean is, right? How am I going to do predictions if I don't know what the mu is? Well, you solve this problem for W, done, and then you go back to this formula that I derived on an earlier slide, and an estimate of mu, which is the MLE estimate, is the average of the response minus the weighted average of your average basis functions computed all the data points. You remember this formula we had before? All right? So once you finish your problem here for W, you can come back to this and compute the mean response mu So basically you have a complete regression function. So in a lots of textbooks actually, they never tell you about this trick, and they go directly to this problem, and they tell you there is no bias term, that you don't have to worry about this and that, etc. The implication is really that quietly they have done this type of analysis and average over mu, so that justifies basically this sort of likelihood model because of this averaging mu and the centralizing of the data. Okay? So, don't, there are different ways of doing it. Again, this allows you to compute W without worrying about the bias term, and once you have W, then you come to this MLE formula and it will give you what your mean response is, and then you're done. I discussed more on the data centering thing, right? So you can read this more. So when you write a computer program, which I will ask you to do, you need to be sure that you do this right. Okay, so let me go to the regression problem and give you some results on a realistic, basically simple case. So our function is going to look A0, that's our bias term, plus A1 times X. It's a 1D problem. The data are actually generated by using this coefficients A0 and A1. I am putting some random noise to them. I am taking the precision on the noise to be given, and also the precision in the prior, I also take it as given. Okay, so lots of interesting things given. So let's see how this problem will work like. So what you see is starting with the prior model, so there is really no data yet. All right, so what we have in this picture is the contours of the prior, which is basically it's a spherical Gaussian. The picture doesn't look good because it will not fit if I put a circle here, but you can, if you zoom out, it's a circle, okay? And these lines, how do I get those? I am claiming here that these are samples from the prior. So if you're going to write a computer program, how do you get samples from the prior? I mean, it's Gaussian. I suppose you know how to get samples. We haven't discussed it. But how do we generate these lines? We have no data yet, right? So these are all regression functions, possible solutions when I have no data. So how do I get those? Well, it's very simple. I sample from this W0, W1, right? Okay? And again, let's forget about the bias term. Okay, so I sampled W0 and W1. And then W0 plus W1X gives me these different lines. So this corresponds to different samples from the prior. Right? Before I collect any data. So obviously, this is a very bad model, right? It's all over the place, so not very helpful. All right, now I collect one data point. So for this X, I know what the Y is. So with one data point, my likelihood looks like this. For that data point, and when I multiply this with my prior, the contours of the posterior look like that. Nice, suddenly I went from a posterior that was a circle to something that is basically, okay, has high uncertainty here, but you notice less uncertainty in this direction. So now we need to sample W's from this posterior, and for this sample from this posterior, I form my regression lines, and I get these lines that are again all over the place, but the majority of them, you notice, passes very close to the data point that I selected. All right? So all of these lines, you see these like they are coming out from this blue point. So now we collect a second data point, so this is the likelihood of the second data point. The posterior now starts shrinking. I have not done actually I haven't formally proved it, right? But you need to trust me on this, and the proof is somewhere on one of the lectures that we may or may not do, but you can actually formally prove that as you collect more and more data point, the posterior uncertainty decreases. you can imagine if that is not the case, right, the whole methodology is baloney, all right? So the uncertainty decreases, and that's what you see here, okay? And you notice the regression lines now with W's sampled from here, they pass through the 2 data points, so they started sort of converging, right? They look nicer. Let's do many data points, all right? Now you can see this uncertainty in these predictions of the regression model. All these are possible solutions, right? And the W's are sampled from this posterior. They look like that. And at the end of the day, if you continue with lots of data points, the posterior becomes a delta function. It's very happy and say, you know, this is my W map, right? That's, you remember the Laplace approximation, a delta function around the map estimate? As you collect more and more data points, the posterior becomes a delta function that is centered around the map estimate. That's the map estimate, okay? And you can see these regression lines. They look very nice. By the way, don't get sort of nervous when your solutions are all over the place like this. The whole idea of Bayesian analysis is, right, that there is no such a thing as a function that fits your data. You notice here you have 2 data points. All these are good functions. We like them. As a matter of fact, if you average over all these possible values, then actually, you know what? Your prediction will look pretty good. It will look pretty good, okay? But here we want to basically show the uncertainty, the predictions, by putting all these lines where W's are samples coming out of the posterior. So there is a computer program that I really advise you to play with it now before I give you homework 3, which is going to be by Wednesday, because that will be a little bit more challenging. So play with this program, and I give you 2 versions, one written by some student in my classes in the past at another institution, and this is the same problem basically from Kevin Murphy's MATLAB toolkit that effectively does the same job, okay? I believe for exactly the same identical problem. All right, so if we have the posterior of W, we mentioned that in the Bayesian context, we don't really care about W, right? W is unimportant. What we're really interested is to do predictions for new input X. So the notation here to clarify it, bold X and bold T are the training data set. Now I provide a new X and I'm asking what is the output. Well, it comes out by multiplying the likelihood and the posterior and integrating W, that this comes to be a nice Gaussian. How do you get this Gaussian? By doing what? You can think of this completing the square in W and using a normalization of a Gaussian, or using directly formulas for linear Gaussian systems, as I highlighted, I think, last Wednesday. But bottom line is, for this problem, the posterior variance comes to be a function of X. So the error bars basically at different X's when you do predictions vary. You expect this, right? In points where you have a lot of data, you expect that to be small. If you have no data, you expect that to be large. And you notice this variance is basically the variance from your noise model, and then the variance coming from the uncertainties in W's in your model, all right? So, and it's additive actually, and it is additive because the model is linear, right? So this is the uncertainties. So for every X, you can say, you know what, for a given X, this is my response. Maybe you're happy, right? That's the mean response. But then you have to go and say, plus minus sigma n. Right? So at every point, you have to give your error bars. Okay? Here is the proof of the previous formula. Again, closing the square or using linear Gaussian system equations. One way or another, this is the nice formula. And actually, since we talked at the uncertainty as you collect more data points supposed to go down. I'm actually formally, I'm giving you a proof on the next slide that this is the case. All right, so you may want to look at this derivation. So if you collect n plus 1 data points, the error bars are less than the error bars when you have n data points, okay? And something also very important conceptually, as n goes to infinity, if you collect infinite sets of data points, the error basically that you're doing, the variance, becomes equal to the variance of the noise in your data. So don't expect basically to have error bars that they are less than the error that you start in your data, right? Doesn't make any sense. Okay? So this is, obviously this will go to 0, and the proof is, you can look actually at this formula here, but the proof is on the following slide. This goes to 0, so you get the variance becomes the noise, and this nice inequality, you can show that it's valid. Okay, so let me, I'm going to give you how the prediction, so once you train the model and you get your W's, like the same problem that I gave you before, how do the predictions look like? So if you collect one data point, all right, so this is, these things here that you see are the error bars, all right? So the error bars, very close to your data point, that's where they're the minimum, okay? But if you go away from your data points, the error bars are huge. Now, all these points that you see here, I suppose, are for plotting reasons, all right? The student who developed this little code, basically he wanted to plot it this, so he evaluated the error bars at different x's, and then he plotted this, these lines that you see here, connected them with straight lines. But effectively, this is for a polynomial of order 9. This is plus 1 standard deviation, minus 1 standard deviation. This is the sign that generated the data, so this is the exact function, right? With one data point, basically, you know what? You can only compute, depending on if you centralize the data or not, the bias or the linear term. So if you add 2 data points now, see immediately how the picture changes. 2 data points, somehow now the uncertainty is small in the neighborhood of the 2 points, but far away from the 2 points is very large. All right? If you don't get this effect, right, whatever method you do, it's wrong. So you basically, if you have no data and somehow you do nice predictions and you say, my solution looks so good, plus minus that, well, no, it cannot be. You cannot make science where you have no information, okay? So this model tells you the error bars are supposed to be big. If you add more data points, all right, so 10 data points here, things look very good. And now, suddenly you see that as you add more data points, you remember the error bars, basically, the variance converges to the noise of your data. And that's why you see now the error bars being basically practically the same everywhere. So for this problem, 10 data points already lots of points. All right? So, you can keep trying. You're not going to do any better. So effectively, you don't need 100 or 1,000 data points. 10 is good enough for this problem, okay? But the nice thing here is, you know what? Here is a nice prediction. This is the mean of your prediction, of your predictive distribution, all right? But if you don't like the mean, you say at any point, I can tell you what the expectation is, but I can also give you the error bars, which is nice. All right, so I need to run. Now, you may say, well, this is from Murphy's toolkit. You may say, how do I measure the covariance of the response at different x points? Well, you do this by basically drawing samples of W from the posterior and then plotting these curves, these regression curves, Y of at x computed with the values W. So what you see here are samples, are regression functions y for different samples w from the posterior. So if you want to know how the solution at this point correlates with the solution at that point, this is the way to do it. You have to basically start drawing samples from the posterior and show it with graphs that look like this. All right. Now we have 20 minutes to do something a little bit more complicated, which is going to be very much related with your homework coming up. So up to now, my notation changes here a little bit, okay? Because lectures given at different times, and I cut and paste them. But I will explain this. So my phi matrix, my design matrix, has become capital X, right? So these are my basis functions, and I put it a note so you recognize it. So so this is my likelihood model, basically, that we had before, okay? But now I want to make this likelihood model more interesting. And I'm going to make it more interesting by saying the noise on this likelihood model is not known. In all the previous results, I had assumed, the noise level. Now I'm going to take this sigma square not to be known. And hopefully, with the exercise we're going to do now, you will appreciate why we spent 2 or 3 lectures talking about Gaussians and conjugate priors and the exponential family, because if you sort of have a good understanding of what we were talking then, the same calculations can be done here. So sigma squared is not known, so we still need to be able to do predictions. How are we going to do the predictions now? Well, your unknowns is not going to be just W, it's going to be W and sigma squared. So before we only had a prior on W, now unfortunately we're going to need a prior on W and sigma squared. Right? We're going to have unknowns W and sigma squared, W my regression coefficient, sigma squared my noise level. So before for W we had assumed a Gaussian. Now if you have a W and sigma squared together, we already have seen this, right? What nice distribution is this? You remember the normal inverse Gaussian, inverse gamma, sorry? Yep. Huh? Yeah. And of course we even did this in multi-dimension, so you can actually do this not only when you have a sigma square there, but you have a whole covariance matrix sigma. Okay, but here sigma squared is a scalar, so I'm going to use a prior for W and sigma squared that is a Gaussian times an inverse gamma distribution. So it's a Gaussian for a given sigma squared and then an inverse gamma distribution for sigma squared. So, all right, it would be nice if when I multiply the likelihood and this prior, I get a posterior for W and sigma squared, which is what type of distribution? Normal inverse gamma, because we already have done this, right? If this is Gaussian, this is normal inverse gamma, this is what you will get as a posterior. So now you say, well, wow, this is complicated, it has all this normalization, blah, blah. No, it doesn't. It's algebra, and if you type it, you're not going to do a mistake. Because if you do a mistake and then you start scratching your submitted homework like that and mark it, etc., we will mark it too and say, sorry, we cannot read this garbage. Our prior model is that it's wrong, and that's the end of it. There's no need for posterior. Okay? So if you multiply the prior and the likelihood, and you try to put this in the form of an inverse gamma distribution, you do actually get an inverse gamma distribution, and these are all the updated parameters. A mean Wn that is given by this, sigma squared here, a scale matrix Vn that is given by that, an inverse gamma with parameters An, Bn, and you notice basically, I think you did this in your homework, sort of the A0 and B0 parameters are updated using information from your n data points. So this is a nice normal inverse gamma distribution, straightforward, exactly. Actually, you can use the results from before and write this with no problems. And also, maybe I think we have shown this before, right? If you have this to be a normal inverse gamma, what actually you can do is you can marginalize and get the posterior of sigma squared alone. This is the marginal posterior of sigma squared. All right? And it comes the marginal posterior to be an inverse gamma, and the marginal posterior of W is very important. It is not Gaussian, it's a student T. Okay? I don't want to philosophize now, but obviously this is an expected result. And why do you care about the marginal posteriors? Well, because somebody will ask you, what are the error bars on sigma or sigma square? You're not going to use this distribution to give error bars on sigma square because this involves W. You're going to use the error bars basically from the inverse gamma and the error bars basically from the student T distribution to compute this. So I am giving a proof of these formulas, even though, again, these proofs are repeat from the earlier slides that we did on Gaussians. Let's push it further. Who cares about W and sigma square, right? Our objective is predictions. So if we had, you know, this, my previous data, I trained the model, I compute the posterior. Now I want a new set of inputs, and now I don't even use one input, but I use basically, you know, if the input is high dimensions, so this is a new input matrix X, curly X, I want to find my responses Y. So, you know, high dimensional input and high dimensional output. So I want to find the responses once I train the model. Well, the answer is not very difficult. So what is, with words, what's the formula on the top does? To get this, what do we do in this equation on the top? What is the first term? What is this term here? I don't hear a thing. And I have to repeat on the microphone of what you said. So what is this term? Is the likelihood for my new data set X curly, Y curly, right? Which is a Gaussian. And what is all the other thing here? Is the posterior for W and sigma square. And what do? I integrate in the parameter space W and sigma square. So how are you going to integrate on W and sigma square? You know, obviously what you will need to do, right, is you're going to need to complete the square in W and come up with some new Gaussian, and then you can say I'm going to normalize it. So you use the normalization of the Gaussian, and then you're going to have to complete, you're going to have to get some inverse gamma for sigma square, so you can use the normalization of the inverse gamma and get rid of that as well. So when you do all of this, all right, the algebra again, for those who type, because if you tell me you're going to write this by hands, good luck. So when you do all of this, and regretfully, maybe for a good reason, you have to use the Sherman-Morrison-Woodbury formula for inversion of matrices that we discussed once upon a time. And I told you this is, it comes everywhere in machine learning and manipulating inverses of matrices. So to be able basically to compute my final predictive distribution, in the last step I have to use the Sherman-Morrison lemma. So this predictive distribution, after you integrate W and sigma squared, comes out and wonderfully is an analytical expression which is a student T distribution. Okay, is a student T distribution. Wn, Bn, etc. Vn are my posterior parameters that you already computed, and this curly X are your new inputs where you want to do predictions. This is a wonderful formula, right? It allows you to do predictions at any input points x curly there, but there is no w, there's no sigma square left. Of course, if you go and use for w and sigma square point estimate, so if you use a plug-in approximation, the results are not going to be very good, okay? Especially the error bars are not going to be very good. 435, this is very much related with your homework that I'm going to give you. So in regression problems, statisticians do lots of weird things, right? And one of those weird things is using this, what's called this Zellner G prior, that seems to violate everything we know about Bayesian modeling. So let me tell you what it is. The previous formulas, very general, use a prior that is a normal inverse gamma, all right? And these are very general parameters. So this Zellner G prior, it says, take the mean in the Gaussian to be 0, take V0 to be some positive constant G times X transpose X inverse, and then take A0 and B0 to be 0, so you get an uninformative inverse gamma distribution. So this 0, this 0, but V0, it is some positive constant X transpose X inverse. Tell me what's weird there. You remember X is our data, the input. So what is weird there that immediately you say, you must be kidding? Nope. There's something very fundamental. This is our prior model, right? And we approximate with this uninformative prior by taking this 0, which is part of our prior, to be G times X transpose X inverse. So the prior depends on what? This is unacceptable. The prior depends on the data. Well, it's unacceptable, but in statistics you can get miracles if things start working, right? So this is called the Zellner G prior, and in the set of many priors that I'm going to ask you to investigate in your computer program will involve to play with this Zellner G prior and derive basically the predictive distributions, error bars, etc., etc., etc. There is a lot of actually reasoning from where this prior comes, but right now, because we did the general formula, you can actually accept that this will be some sort of an uninformative prior, for sure, for sigma square, and obviously if G is very big, right, you can see the variance in the normal is very spread, so it's really a nice uninformative prior. Okay, a few more uninformative priors. All derived from our general formula, and all of them have significance in regression problems. All of them come from this normal inverse gamma distribution. So here is a popular uninformative prior for W and sigma square. You take the mean in the Gaussian to be 0. You take the variance to be infinity. And as before, you take the coefficients A0 and B0 in the inverse gamma distribution to be 0. So if you substitute, this comes to be sigma to minus D plus 2. This is the dimensionality of the problem. Okay? It's so usually if you were getting, and we will see this here, sigma sigma minus 2, you already have seen that. You remember when we're talking about scale invariant priors? So we already have seen this sort of uninformative priors, but now from our general problem you get sigma to minus D plus 2. What does it take to get a prior that looks like 1 over sigma square? Where what you need to do is you need to assume that W and sigma square are independent, and then take uninformative priors for W and sigma square independently, so you make this uniform sigma squared, then you have to use 1 over sigma squared. So this is another sort of uninformative prior. And again, both this and this model, you can derive it from the very general normal inverse gamma by plugging in the right parameters. You really have to dig in the literature to find these results, here and there, and in lots of places where some of these results are being copied, you will see lots of typos and lots of mistakes, and you try, and a month later you realize it was all wrong. So again, it helps typing and looking at this once a while, right? And then they come and they say, yeah, I'm right or I am not. Okay, so what you will need to do on the for this sort of different type of priors, you're going to need basically to solve a high-dimensional regression problem. You will plot error bars, and actually you will compute credible intervals similar to what you did when you're doing on homework 2. I'm not going to tell you what the precise problem is, but I'm going to give you a specific sort of data set to work on this. Okay, we have 4 minutes, so let me put in place the subject for for Wednesday. So we will cover this on Wednesday, and then we're done with sort of regression problems. So let me go on this slide. So you remember we're talking about the hierarchical Bayesian models, right? Don't pay attention to M. M refers to one of our models, one selection, let's say, of basis functions, or maybe on the selection of the number of basis functions. So M refers to a model. But let's say W is the same what we had up to now, all right? So in a hierarchical model, we're going to put some hyperparameters eta, and then we're going to put some prior on eta. So in our simple spherical Gaussian noise problem, etc., can you tell me what are the hyperparameters that we consider fixed in our problem? Like what parameters? You remember I gave you lots of plots. What were the hyperparameters that we took them as fixed? How about the noise in the data? Was that fixed? That was one. What else? In the prior, you remember there was a precision or variance, alpha. We also took it to be constant. So there were a few parameters that we took them to be constant. So really what you need to do is you need to actually compute, if you want to be serious, the posterior of those parameters as well, the same way we did integrating, sigma square out, in the last few slides. But obviously you cannot do this for every problem, all right? So these Bayes models that we gave as an approximation to this issue of hierarchical Bayesian models involves solving this optimization problem. So can you remind me, what was the idea? What did we supposed to do with parameters eta? We're not going to compute the posterior. What's the best alternative we can do on this unknown parameter eta? To integrate means you need to know the posterior, which we don't want to compute because it's very difficult. So what is then the next alternative? Obviously here you can say, when it says maximize, means we're going to treat them as point estimates. So we're going to fix those parameters to some point estimates and use those in our predictions, and those point estimates are going to be computed by maximizing what? Which in essence you can see on this equation as well. So those point estimates will maximize what? The only thing we know is data, right? And the evidence of the data, which is, you remember the denominator in the Bayes rule is the marginal, is the likelihood. Is the likelihood of the data, P of D, okay? But here, because there is W here, we're going to compute eta by maximizing what evidence? The marginal evidence where W has been integrated out. So what we're going to do on Wednesday, for the simple example that we discussed with the spherical Gaussian noise and prior models, effectively we're going to compute this marginalized evidence, and we're going to compute the parameters that maximize that evidence. That calculation, again, falls under this formula. It is the suggested way to do in hierarchical Bayesian models, and it is done in the context of regression, classification, practically many machine learning problems, okay? So I'm going to be in the office for office hours. This is your last call for questions regarding the homework set, regarding projects. Don't assume that I'm going to be around every week, because I need to do some traveling in the forthcoming weeks, right? That's why we had some extra lectures. So please do take advantage of office hours, okay? My office is in Cushing, 311I, because somebody told me that it was placed on the other side of the building, okay? So I will see you at office hours, and that's the end of the lecture today.